This is the problem solving series. Okay, and I'm your teaching assistant for the thermal physics course that is taken by Professor Demallo Banerjee at NPTEL in this semester. So this problem series is mainly conducting for to solve your assignment problems, okay, and also clear your doubts. I also discuss the problem that is reached in the discussion forum. Okay, and so before I'm going to discuss, so let's first briefly talk about myself. Briefly talk about myself. So I'm Subrat Samanta and a PhD student in the Department of Physics at IIT Kanpur. So my research focuses on the high energy physics and the theoretical aspect of high energy physics. So yeah, so if you have any questions, you can ask directly in this problem solving series. So this problem solving series I'm conducting every Sunday at 4 p.m. and you also raise your questions in the discussion forum. I will answer these questions there if time permits. Otherwise, I will definitely discuss these questions in this live sessions. Okay, and you can also ask directly if you have any doubts. Okay, here. Okay. So I mainly discuss the weekly content. Okay, some of the basic concept in this week. Okay, that is already uploaded in the uploaded in the NPTELs. Okay, so I will discuss some basic concept and solve some problems that helps you to solve your assignment problems in the upcoming week. Okay, so let's first share my screen, and then if you have any questions, you can ask. Okay. I hope my screen is visible now, right? Yeah, I hope my screen is visible now, right? Okay, so there is a one questions that in the discussions forum. First, I will discuss these questions and then I'll so just a minute. Okay, so there is a questions that in the discussions forums that you have written df dx dt equals to number density times dA Vx dt. Let's first share these questions if it possible. So share screen. Yes, my screen is visible, right? Hello. Okay, so there is a questions that is so I have questions about what is happening in this video. So the question is basically you have written df x dt equals to number density times dA Vx dt times delta px. We know that force is equal to mass times accelerations. Mass equals to density times volume. What is left is accelerations, but in the above equations we have written the change of momenta in place of accelerations. I don't understand it. Okay, so so the problem is basically the confusing about the density, right? So the mass density and the number density, they are two different things. Okay, so now I will explain in details. So wait a minute. Yes, so basically the questions is about this. So if you have a wall, let's say this so this one is the wall, so this blue marked. Okay, so this is the wall. Okay, and this is the x directions, let's say wall, and if I consider a small element dA, Okay, and the velocity in this directions, x direction is the vx. So at dt times the velocity, the distance is basically this distance. Okay, so this one, this is the distance, this is basically vx times dt. Okay, so for an elemental area dA, that is on the wall or the surface, okay, on the walls, so the force is basically dfx times dt in time dt. Okay, so in time dt, the force on the elemental area dA on the wall, so is basically dfx times dt. So this is equals to n times dv. Dv is the volume element, so is the volume element, and n is the number density, right? And delta px is the change of momentum. Okay, so now if you consider a scenario where the particle or the molecules hit to this wall, okay, let's say in theta directions, and after hitting the back, okay, this is the also theta directions. Okay? Because this is a elastic collisions. Okay, so the hit to the walls is basically a elastic collision, so they hit the wall at angle theta from the perpendiculars, and also I think back to the same angle theta. Okay, so because of this, only x, I mean if this is the x directions, so the change in momentum is only x. Okay, other as cancel, y component cancel, z component cancel, only the x component are left. So basically m vx is the momentum in the x directions minus m vx. So only x component are left, y and z component cancels because the collisions are elastic. So its total is basically 2m vx. So during this process, okay, the change in momentum is 2m times vx. Okay, so now if we write this, so dfx times dt equals to, so this is the number density. Okay, so this is basically I can write n, the total number of particles if the in the container is n, and is the total volume is v. So this is the number density times the small volume element dv, that is basically dA, the area element, and the distance vx times dt, right? So t times the distance basically cover vx times dt because the velocity is vx. Okay, so this one is your total dv, and times the change of momentum 2m times vx, right? So this is basically, n by v and 2 vx square 2 m vx square and dA times dt, right? So now if you know that f equals to ma, so f equals to, let's say, ma. So here m is basically n times m, right? So n is the number of molecule and m is the mass of the molecules. Okay, every molecule. So total mass is basically n times n times acceleration. So accelerations, we know that this is basically d vx over, let's say, dt. Here the a, so is basically vx over t. Okay, so if we consider dt time, so it's dt, right? So this is basically if we calculate the dimension, so f dt times nm times vx, right? So here it is so now here if we match the dimensions, so basically n times m, and you have an area and this is a volume, right? Okay, so this is basically yeah, so this is basically dt divided by so this one is a volume, and we can also make this vx dt. Yeah, so one of the vx dt is basically length, and dA times Vx dt is basically dV. So dV by V, this is dimensionless, and left is Vx, right? So this is again n m Vx, and this one is the dimensionless number. Okay, so this is consistent with F equals to ma, because this n is the number density, not the mass density. Okay, mass density differ from the number density, right? Mass density basically m by v, not n by v. Okay, so that is the confusions in the questions, that so the density is not the same as the number density or mass density. You have to specify. Okay, so now you have any further questions, you can ask. Okay, please ask if you have any questions on the content, weak content, or in the assignments. Otherwise I will solve some problems from the assignments. Okay, so let's first discuss some basic concept. Okay, uh, so first of all, so this is a thermal physics course, right? So what do you mean by thermal physics? I mean, what is the thermal physics? Okay, I mean, what to learn from the thermal physics course? So thermal physics is basically a concept of large numbers, right? So why large number appears in the thermal physics, right? So if you look into this thermal physics problem, so there is always large number appears, right? And this is basically physics of large numbers. Okay, and the concept of large numbers. So, okay, so if you consider a, let's say, one bit of matter, right? So let's say 1 mole of carbon, right? So how many molecules or how many atoms are there in 1 mole of carbons? So basically 1 bit of matter, I will call that 1 mole of carbon C. Okay. So 1 mole of carbon, how many atoms are there, right? So basically, yeah, so the Avogadro number, right, is the order of 10 to the power 23, right? So 6.022 times 10 to the power 23 number of atoms, right? So 6.022 times 10 to the power 3 number of atoms. Right? So if you consider a bit of carbon, that means 1 mole of carbon, that contains order of 10 to the power 3 numbers, right? So that's why you are dealing with a very large number. Okay, and how to deal with this very large number, that is basically thermal physics. Okay, we learned in this course that how to deal with the very large numbers. Okay? And one more thing is that so many thermal physics problems, okay, also involves the commutatorial factor, right? So basically the probabilities. Okay, so the commutatorial factor is basically, let's say we consider a omega, that is basically n, the number of particles c, and r rates. Okay, so let's say small ncr, right? So this is a commutatorial factor. So now if you want to calculate this, so this is basically n factorials, r factorials, and n minus r factorials, right? So here the factorial scheme, right? Now if we imagine that, let's say if you calculate 2 factorials, that gives 2. If you calculate 3 factorials, so how to calculate factorials is basically 2 times 2 minus 1 is 1, so it gives 2. And if you calculate 3 factorials, it's basically 3 times 3 minus 1, 2, 3 minus 2, 1, so it's basically 6. And if you calculate 4 factorial, it's basically 4 times 4 minus 1 times 4 minus 2 times 4 minus 3, right? So this is basically gives you that 4, 3, 2, 1, so it's 24, right? So just look into this changing. Okay, so 2 factorial 2, 3 factorial 6, and 4 factorial 24. Okay, So now now I will tell you that, okay, so if you want to calculate, let's say 10 to the power 23 number of particles and factorial of this. Okay. So this is a very huge number. Okay, how to compute this? So in your calculator, it's a pocket calculator that you are using, you cannot calculate after 70 above 70 factorials. You are getting I think overflow error, because the 70 factorials is greater than approximate about 10 to the power 100. Okay, so it's a very huge number. Now if you want to compute the 10 to the power 23 and the factorial of this number, okay, so how do you compute this? This is a very large number, and in your thermal physics problem, this kind of factorials came into the pictures. Okay, so how do you compute these things? Okay, so that is one of the very challenging tasks. Okay, because if you using any calculators or things, there is overflow error, so you cannot compute above 70 factorials or 100 factorials. So it's a very huge numbers. So then there is also, I mean, catch that there is also approximation that is called Stirling approximations. Okay, so Stirling approximations. So these approximations tells you that, so when this large number of factorials comes, so the came with a logarithm, right? So ln, let's say 10 to the power 23 factorials, right? So this is basically, that gives you that 10 to the power 23 times ln 10 to the power 23 minus 10 to the power 23. So this is approximations. It's a very good approximations if n is very large. So now in this case, my n is basically 10 to the power 23. So the general formula is it's ln n factorial, it's n ln n minus n. Again, this is approximations. Okay, and also this is an approximations, and this is true for very large n. Okay, true for very large n, right? So in this case, we are considering n is 10 to the power 23, so you can use this one. So if we use this, it's very, now it can easy to compute. Okay, because so ln 23, we know that 23 times ln, so this is basically equals to 10 to the power 23 times 23 ln, so this is basically ln base e. Okay, and that is 10 and minus 10 to the power 23. Now we can compute, okay, in your calculators. Okay, so this kind of I mean approximations you have to use in order to compute this very large numbers. That is commonly appear in your over the course, okay, in your thermal physics problems. Okay, so yeah, so far any questions? Okay, if not, so I'll going to be discuss some basic concept about the kinetic theory of gas. So this is the problem of large numbers. Okay, now what is the kinetic theory of gas? Then I will solve some problems related to the kinetic theory of gas. Okay, so and one more thing, that all the sessions will be recorded and provided you to all by next 1 or 2 days. Okay, so you will get the link, YouTube link, and you can watch anytime. Okay, and if you have any questions, you can also ask in the forums or the next sessions. Okay? So the kinetic theory of gases. Now what is the basic motivations of the kinetic theory of gases? What is actually mean this theory? What this theory actually tells you? Yeah, so the kinetic theory of gases basically yeah, so basically is the determinations of the properties of the gases. Okay, So I want to determine the properties of the gases. That's why I use this theory. And yeah, so kinetic theory. Okay. So if we determine the theory of gases, okay, but how to determine the theory of the gases? So basically, so the kinetic theory of gases tries to determine, so it tries to determine the properties of the gases, okay, properties of the gases by considering, okay, by considering the probability distribution. It is very important. By considering the probability distributions associated with the motions of individual molecules, associated with the motion of individual molecules. Okay, so listen very carefully. So the kinetic theory of gases tries to determine the properties of the gases. So I want to determine the properties of the gases by considering the probability distribution associated with the motion of individual molecules. So let's say we have a consider a box, okay, contains n particles, okay, and these n particles basically n molecules, and I want to determine, so this is basically a gas, okay, gas chamber that contains n molecules, and I want to determine the properties of the gases by determining the probability distributions for every n molecule, for molecules, okay. So if there is n molecules, I want to determine the probability distributions of a one particle motions, and that is same for all n particles, okay. So that is the kinetic theory. So now there is a very basic assumptions, okay. So what are the assumptions for the kinetic theory of gases? So in order to do that, so there is some kind of, we make an assumptions, okay. So the assumption is that the first assumption is that when you consider that each molecules are independent, that means they are not interact with other molecules, right? So that means each molecule, it's not interacting with other molecules, it's not interacting with other molecules. So now you may ask the questions that, so the molecule is not interacting, then how to determine the properties of the gases, right? So the molecule is not interacting with other molecules by any forces, right? So by any interacting forces, interacting forces. So there is a no interactions between the two molecules inside the gas chain, okay? But the molecules can collide with other molecules. So molecule can collide but not interact. So there are two different meaning, okay? So collisions and interactions. So if we have a, let's say, 2 points are interact, that means there is some kind of force between the molecules are there. So that's why they are interact via these forces. But if there is no force, but they can collide, okay, because these motions of the particles and the b motions and the b particle motions, okay, they can collide, okay, because they are random, okay, so they can collide. But the particles can collide. And also there is a catch. So if the particles are collide, okay, even if there remains in thermal equilibrium, So if the two particles are collides, but the temperature does not change. Okay, so basically the thermal physics again is the is the basically a macroscopic properties of a system that determines the macroscopic properties of the systems. So let's first let's slightly deviate from this. What is the actually thermal physics? So the thermal physics determine the macroscopic properties of a system. Okay. So this determines, so this is basically a side note. It's basically the macroscopic properties of the system. Macroscopic properties of a system. Okay. System means the, let's say, container of gas. Okay. So what are the macroscopic properties? It's basically the temperature, right? Pressure, volume, this kind of things. So now when you consider that the particles can collide, but the temperatures of the system, that means whole of the gas chamber, okay, remains same. Temperature does not change. So the particles can collide, but in equilibrium, in thermal equilibrium. I will discuss what are the thermal equilibriums later, but now on, you just remember that the thermal equilibrium is basically the temperature does not change. Okay. So, but in the thermal equilibriums. So, where the particles can collide, but in thermal equilibrium. Okay. So, this is the one of the basic assumptions. Now, we can compute. Let's say then what is the, let's say, energy of each molecules, and how to compute the energy of an each molecules. So, let's say basically a container that contains, let's say, n molecules. Okay, let's say n number of molecules are there, and its temperature T and its volume V. So this is the container, volume V, and the temperature is T, and the number of molecules n. Now I want to compute the energy of, let's say, this molecule, the red dot. Okay. So when you compute the energy of this molecule, the other all n minus 1 molecules, so this basically, yeah, so the other n minus 1 molecules, so these contain n minus 1, and this is your, let's say, identify the molecule is A molecules, okay, and other n minus 1 molecules at temperature T, okay, because your whole temperature is remain same. So now basically you just a concept of equipartitions of energy. So the molecules, the energy of this A molecule EA is basically half kBT, okay, because the T is basically the temperature of the system, okay, that is remains in thermal equilibrium. And if I want to say that what is the energy of these A molecules, single molecules, that is half kBT. Similarly, for if you consider any other molecules, okay, that is also half kBT. So the total energy of the system, E total, is basically n by 2, because if there is n molecules and all molecules you can treat it as a same way independently, so it's n by 2 kBT is the total energy, right? Yeah, so far any questions? So that is basically the equipartitions theorem. So each molecules have the same energy. So, and also the more precisely tells you that the each degree of freedom. Okay. So let's say if there is a f is the number of degree of freedom, number of degree of freedom, then the E total is basically f by 2 cavity, right? So now can you tell me this one is the right or wrong? Okay, so far I considers the, let's say this one is a container, that is a one dimension, but if you consider a volume, let's say box, that means each molecule can also move in the three directions, x directions, y directions and the z directions, right? So that means when I say that the EA, this is not half cavity, right? If you consider a 3D box, okay, that means that each molecule can also move in the three directions. Okay. So that is basically a 3 by 2 cavity. Okay. Because the equivalence says that the energy is divided by each degree of modes, okay, or each degree of freedoms. If there is n particles, that is basically 3n times half cavity. Okay. But each particles there is a 3 degree of freedom. Okay. Because they can move in the x directions, they can move in the y directions, they can move in the z directions. Okay. So at any arbitrary directions, we can decompose into x, y, z, because our coordinate system is a 3D coordinate system, x, y, z coordinate system. So I can define any points in terms of x, y, z. Okay. So basically that is the degree of freedom. So the minimum number of independent parameter that is needed to describe the systems, okay, at any points, okay, in the space. Okay, so that then this is basically f. Now for in the case the f basically 3n, okay, and for general systems it's basically f by 2 cavity. I will discuss also some other problems, okay, that helps you to solve more complicated scenario. And yeah, so far any questions? This is a very crucial. I mean, you have to understand that how to compute the degree of freedoms, and then you can calculate the total energy using equiperson's theorem. Later I will discuss that how this half cavity came, okay, why the each degree of freedom share the half cavity, not 1 by third cavity, not 1 by fourth cavity. Okay. So this is also a very specific, I mean, scenario that we are considering, that's why this half cavity came. Okay. So if we consider some other situations, there might be a 1 by third cavity, 1 by fourth cavity. Okay. So but in kinetic theory of gas, okay, so it's basically precisely half cavity for each degree of freedom. So, and these are the assumptions. And also the another assumption is that so this is not an assumption. Yeah, so if you have any questions, please ask. Yeah, I will discuss. It's basically 1/3 cavity if depends on your distributions. Okay, so if your particles, let's say not a v, I mean, so the motions of the particles. Okay, so this is basically computed from the motions of the particles. If the particles follow the distribution that is proportional to v square, okay, you don't understand, right? So basically they are what is your energy for a particles if there is no potential? So kinetic energy, right? So half m vx square, right? And similarly if you consider half m Vy square in the y directions and the kinetic energy in the z directions, half m Vz square for a single particle, right? So this one is, let's say, for a particles. Okay, so I am not considering any potential, that means any interacting force. So they are only a random movement through the kinetic energy. Now each modes have a Vx square Vy and V square times term, right? So due to this square, so they are basically share half cavity, right? So this one is a half cavity, this one is a half cavity, this one is also half cavity. Now if we add this total is basically 3/2 cavity for each particle, for each molecules. Okay. So this half is basically comes for this V square. Okay. This V square. Now if you consider a potential, let's say they interact through a potential that is V to the power 4, right, or x to the power 4, then the energy also share 1/4, right? But in this case there is only kinetic energy, so that's why they share half cavity. Okay. Okay, so yeah, now it's, I hope it's now clear, right? Or if you have any further questions. Okay, hope it's clear now. So now what is the distributions of the particles in the kinetic theory? Sorry, there is another assumptions that, yeah, so this one is the one assumptions, and the another assumption is that is to, yeah, so that the size of the container is large. Okay, so the size of the container is also large. Size of the container of the system is large. Okay, I mean the V is large, let's say the volume, so volume large. So why we make these assumptions? Such that any fluctuations between the particles are neglected. Okay, we don't care, because if you're, let's say, contain n particles and in very large volumes, okay, if some particle fluctuates, okay, so you can totally ignore. Okay, you can ignore. So the fluctuations of the molecules can be ignored. Okay. So now what, with these assumptions, what is the distributions? So first of all, I wrote this. Okay, yeah, it tries to determine the properties of the gases by considering the probability distributions. So now we come into this point. What is the probability distributions of the molecules under these assumptions? Yeah, so I hope all of you learn, I mean, already seen this kind of distributions, that they follow the distributions is basically if V, where V is the velocity, is a times V square times e to the power minus V square, right? So 1 is basically proportional to V square, and there is an exponential factor. Okay, where V is the velocity. So remember here V square is basically Vx square, Vy square, Vz square. If you consider a 3D, three-dimensional box, okay, so your V square is basically Vx square, Vy square, Vz square. Similarly for x, I mean, if you know r square equals to x square plus y square plus z square in 3D coordinate system, Cartesian coordinate systems. So in this case also, for the V square, you can also write this. Yeah. So now what is A and B? So this B is basically m over 2 kbt, right? And A, yeah. So now I want to compute A. Let's say first the B is given. Okay. Okay. So now if you compute that, what is the maximum probable speed, okay, of the gas molecules. I want to give the distributions, that is the gas molecule follow these distributions. Okay, I want to calculate what is the maximum probable speed. So let's first draw this distributions. Okay, so this is your f of v and this is your v. Okay, so if you draw, it's basically v square and then exponentially decay. Okay, so the maximal speed, where, so this is your maximum speed at some velocity, let's say vmp. Okay, because at this point vmp, your f of v is maximum. Okay, so that is the maximum probable speed. The corresponding velocity is the maximum probable speed. Now how to compute this? So that means this is an extrema. Okay, I know this is a maxima, but this is an extrema, right? So the conditions of the extrema is basically df of v over dv equals to 0. This is true for minima as well as maxima. This is true for extrema. So this is 0 at, let's say, v equals to vmp. Now I want to compute vmp. I do not know what is vmp, but I tell you that at v equals to vmp, this thing is 0 from the distributions, but I do not know what is vmp. Okay, that's I calculate. So if you take on derivatives and if you get vmp is basically square root of 2 kBt over m, that is basically 1 over square root of p, if we consider this p. Okay, now if you calculate, now I don't know this is the minimum or maximum. Okay, so if you compute that, okay, so d2v, the second derivatives, over dv2 again at v equals to vmp. Okay, so now you know what is the vmp, your 1 over root v. So if you calculate this, and you can easily check that this is the less than 0. That means this is an extreme, this is an maximum. Okay, not a minimum, because the second derivative at this point, at this values of vmp is less than 0. Okay, so this is your homework task. You just check this. Okay, and the more importantly that the vmp is proportional to 1 over square root of b, where b is this scaling. Okay, okay, so now I will solve some assignment problems. So yeah, so far any questions for the understanding? Okay, if no more questions, then I will discuss some assignment problems. So there is a problem that is basically 1 mole of, so okay, so 1 mole of carbon means okay, so 1 mole of carbons is basically, what is the atomic weight of carbon? Atomic weight, so AW, atomic weight of carbon is 12, that is 12 mu, right? And 1 mu is basically 1 over Na number of gas, right? So this is basically 1 mole of carbon is basically 12 gram of carbon. right? Okay, so yeah, so 1 mole of carbon is basically 12 gram of carbons, and so if there is a Na number of C carbons, Na of C, so the Avogadro number Na is the Avogadro number. Okay, so it's basically Na times 12 mu. Okay, right? So this Na times 12 mu is basically 12 over 1 mu is 1 over Na gram, so it's basically 12 gram. Okay, so it is clear not, sorry, it's 12 gram. So 1 mole of carbon is basically 12 gram of carbon. So in this way you can just check that. So 1 carbon is basically 12 mu because atomic weight of carbon is 12 mu. Okay, and Na number of carbons is equals to Na times 12 mu, and if you know 1 mu is basically 1 over Na gram, so it's basically 12. So similarly, if you calculate the 1 mole of NaCl, okay. So now what is the formula weight of NaCl? So NaCl is basically a compound that Na plus, okay, and plus Cl minus. Okay. So in this case, we compute the formula weight, not the atomic weight. So what is the formula weight of Na? Is 23, and what is the formula weight of Cl? Is basically 35, right? So therefore 1 mole of NaCl is, now 23 is the formula weight, so 23 gram plus 35 gram, right? So total 58. So when you consider carbon, for this case you have to consider the atomic weight of the carbons, but in case of compound, let's say NaCl, in case of the, we can first compute the formula weight and then just translate into a mole. Okay, so 1 mole of NaCl is 58 gram. Similarly, if you say x mole of NaCl, x mole of NaCl is basically 58 times x gram. Right? I think all of you know that 58 times x gram. Okay, for x mole of NaCl. Okay, so another problem that is related to ideal gas. Yeah, so I think everyone knows that what is the equations of an ideal gas. So it's basically PV equals to N kBT, right? So if N is a Avogadro number, if N equals to Na, then only PV equals to RT, because Na kb is R. Okay, Sarvojinin gas constants R equals to Na times kb, but for any other values of N, it's N kBT. So you can write this P as N over V kBT, right? So this is basically a number density, okay, small n, So small n times kBT, and we can write the temperature T is basically pressure. So here is P is the pressure, okay, not the momentum. Okay, so this is very confusing. I mean, just write this is a pressure. Okay, so pressure P over N kB. Okay, so now if P is given, so let's say in your problem N is given. Okay, let's say SI unit, and P is the pressure is given. Okay, again in the SI unit, you have to change in one unit always. So I follow the SI units, and you know the kB value is 1.38 times 10 to the power minus 23 joule per Kelvin in SI unit. So then you can calculate the temperature T given NP, and you know the values of the kB, so you can calculate the temperatures in Kelvin. Okay. Yeah, so we just use your calculator and compute this temperatures. And the third problem is that the RMS velocity. Okay, so the RMS velocity, so here is very important. So in this case we get the most probable velocity is the square root of 2 kBT by m, right? But the RMS velocity for these distributions, so for this velocity distribution, say v is a v square e to the power minus b v square, okay, where b is the square root of 2 kBT by m, square root of 2 kBT over m, and if you compute the v RMS velocity, so this is basically 3 kBT over m. Okay, okay, so this is basically 3 kBT over m, and yeah, so this formula derived in the class, so I am not going to the details, I just use the formula. So v RMS is basically 3 kBT by m, and so in this case, so if you multiply both sides with 3 NA kBT over m NA Avogadro numbers, so multiply both sides with the Avogadro number, so this gives you NA kB is basically 3 RT over MNA is the total mass. Okay, right, so that means v RMS is proportional to square root of T, where R is constant, M is given, and total molar mass. Okay, that is already we know that for a fixed, and this vary with the temperatures is for a fixed molar mass. This vary with the temperature square root of T. Okay. So now if we have two temperature, let's say T1 and T2, okay, and we have to compute V RMS per 1 divided by V RMS per 2. Okay, so this is basically square root of T1 and T2. Other things are cancelled. Here I use proportionality, now I use equals, because all other R is constant, so same, and M is also same, but the temperature are different. So then we can compute the ratio VRMS 1 over VRMS 2. So let's say this one is a 1, this one is the 2. Okay, so this is basically yeah. So now if we say that T1 is basically, let's say 1 over 42, okay, then VRMS is basically 2. or if this is given, let's say this one is given, then your T1 is basically 4 T2, right? This is given. So ratio of the RMS velocity is given, so you want to calculate the temperature. Okay. Similarly, if there is a same T, if the temperature is same, if say another thing, if temperature is, let's say, same, then V RMS, let's say for NH3 molecules and V RMS for H2 molecules at same temperatures, I want to calculate the ratio of two molecules NH3 and H2. Okay, the ratio of the RMS velocity of these two molecules at same temperatures, right? So it basically gives you that square root of, so it proportional to 1 over square root of m, right? So if temperature is same and R is Chauvet-Lyapunov gas constants, okay, so universal gas constants, and if temperature is same, then it's proportional to 1 over m. So that means m over H2 divided by m over NH3. Now if this is given, it is easy to compute, okay, straightforward. So the concept is that V RMS is proportionality 1 over square root of m. Okay. So you can, using this formula, you can calculate several problems. Okay. Just switching the values of m and t. So similarly, if you calculate the average velocity, so this is basically the average. So this one is the RMS, and VMP is the most probable, and another is the average velocity. Okay, so average velocity is, the formula is 8 kVt over pi m. So all are I think proportional to square root of t and 1 over proportional to square root of m. Okay, and proportional to 1 over square root of m and proportional to t. So all most probable velocity, RMS velocity, as well as the average velocity, but the coefficient are different. Okay, so let's say for a t equals to 300 Kelvin, that is already given, and you want to calculate the average velocity of H2 molecules. Okay, so this is your questions, that calculate V average of H2 molecules at t equals to 300 Kelvin. Okay, so how to compute? So first of all, calculate mH2. So mH2 is that 2, so H2 molecule is 2 gram per mole. So 1 mole of H2 is basically 2 gram. So that gives you the 2 times 10 to the power minus 3 kg per mole. Okay, I converted to SI unit. So now we know that the P average is basically 8. If we multiply it with the Na, both numerator and denominator, so 8 RT over pi, pi and capital A, capital MH2. So now what is the values of R? It's 8.314 times, yeah, so joule per mole per Kelvin, right? So if you plug into this, so this is basically 8 times 8.314 times temperature is 300 Kelvin, and mH to pi, if you know values of the pi is 3.14. Okay, I'm taking only two digit, okay, times what is mh2 is 2 times 10 to the power minus 3. So note, I use always SI unit, okay, through both numerator and denominator. So then, so this basically gives you that 1782.5 meter per second. Okay. So please check this. Okay. Now, if you want to compare that, okay, so last one is I want to compare that. So I know that there is three type of velocities. One is the average velocity, let's say v average. So that gives you, you just compute, and another one is v RMS. Okay, another one is v MP, most probable velocity, right? So which one is larger? Okay. So both vary. I think the temperature dependence and the mass dependence are same, right? But the coefficients are different. So now I want to quantify which one is larger. Okay, but what is the order? What is their order? Okay. So you just I mean look into the coefficient. So V average is basically 8 R over pi. In this case, T over H2. So yes, so it's 3R, square root of 3R, and this is most probably 2R. Okay. So let's check. Yeah, so B is equal to 2 kBT by M, so 2R. Okay. So now you just compare. So it's basically this one is the largest, okay, and then this V average, then VMP. Okay. So basically the order is that V MP is smallest, and then V average, then V RMS. Okay, so this is the things, and if you draw a velocity distributions at a particular temperature, so in the graph, let's say I have a exponential. So this gives you e to the power, let's say, minus b v square, and this is your let's say a v square. Okay, and your f of v is a v square times e to the power minus b v square. It's basically multiply of these two curve. Okay, so you just multiply these two to get this. So the maximum is here, then something like that. And so the maximum point is basically this point. Okay, so they must pass through this point. Okay, and this is your VMP, and your V average just after this point. I can use another color. So here something here is that your V average. So this is your V average, and something here, this point is V RMS. Okay, so order is basically in this order. Okay, so all things after VMP. Okay, yeah, so now if we if you want to know what is the values of this constant A and B, so I already told you that B is basically m over 2 kBt and A is m over 2 kBt over 3 over 2 times 4 by 4 over square root of pi. Okay. So now if you draw a curve, so VMP again it is proportional to square root of t. Okay. So if we draw a curve, so that is two different temperature, let's say one curve at T1 versus this curve is T1. Now I want to draw a curve for T2. Okay, I want to draw a curve for T2. So this is, let's say, f of v over v. Okay, and the T1 is greater than T2. Okay, now I want to draw a curve for T2. Okay, how to draw? So first check that, okay, so VMP is large or small for T2 is greater than T1. So that means, let's say for T1 curves, okay, VMP somewhere here. So let's say VMP1. For T2 case, if we check the ratio that VMP2 over VMP1 is basically square root of T2 over T1, that is already greater than 1 because T2 is greater than T1. So that means VMP2 somewhere here, let's, okay, VMP2, okay, so that means the curve must have a maxima at this point. Okay, now the second one is that what is the values of the maximum. I know where is the maximum, but now what is the values of the maximum? So this peak, okay, so here is the value is basically f of v mp, right? So this value is f of v mp1, right? Right? So f of v mp1. Now the constant f of v also contains a, because f of v is basically a times v square to the power minus v square. So now a is inversely proportional to the temperatures. It's not proportional, it's, I mean, proportional to t to the power 1 over t to the power 3 by 2. So your f of v is proportional to a, that is also proportional to 1 over t to the power 3 by 2, right? But this is also v square, right? So if we just I mean, draw into that, okay, so f v mp, okay, this is basically 1 over t to the power 3 by 2 and vmp square. So vmp square proportional to temperature, so 1 over t to the power 3 by 2, and this is t, okay, this is basically 1 over t to the power half, right? The other one is just a order 1 number, so e to the power minus bv square is a order 1 number, okay, so e to the power minus just 1, okay, you can just easily check, okay. So it's basically ultimately the temperature dependence 1 over t to the power half. So that means if we increase the temperatures, okay, your values of the maxima, okay, so at maxima what is the values of the functions, it also decreases. So that means the curve is basically goes like this, maxima there and then, so maxima is also decreases. So the maximum point increases if the values of the functions at the maximum is less, because that is inversely proportional to square root of t. Okay, so this is for t2. Okay, for t2 is greater than t1. So when you draw a curve, I mean the distributions for a different velocity or different different temperatures or different molar mass. So you first consider the points where the maxima shifted or left or right. Okay, I mean the increases or decreases, and the values of the function increases or decreases. Okay, if you note these two things, you can draw a curve. Okay. Okay, I hope it is clear now. So if you have any questions, then please ask. Yeah, so far any questions? Okay, so now I'm going to discuss the linear molecules, that is more than two particles, two atoms. So let's say linear triatomic molecules. Let's consider linear triatomic molecules. Okay, so the molecules is basically I mean it's placed in this form. So we have a one molecule, another molecule, and have along a line. Okay. So let's say this is molecules. So trilinear molecules, okay, linear triatomic molecules. Okay. So three atoms in a molecules. Okay, and it places in this. So what is the degree of freedom of this molecules? There is a three atom, okay, in the molecules, and they are placed in the linear. Okay. So what is the degree of freedom? Let's say temperature T is 300 Kelvin. So what is the degree of freedom if the degree of freedom okay. So what are the translational degree of freedoms? First of all, I want to discuss the translation. Okay, so in 3D space, so they can translate. No, why there is a 2? Because in 3D space the whole when each atom is, yes, so the translational degree of freedom is 3 plus what are the rotational degree of freedom? So the rotational degree of freedom is 2, right? And what are the vibrational degree of freedom? Yeah, vibrational mode, because I consider temperature at 300 Kelvin, so that means they can vibrate. So that means this, the middle one, so middle one, the atom is in the middle. Okay, they can vibrate. Okay. So the vibrational degree of freedom also 2, right? Because they can either vibrate this way or vibrate in this direction, right? So it's two mode. Okay. Yes, for 1D. Sorry, I mean this can hybrid this way, right? Why there is a two mode? I mean why I consider two for the vibrational degree of freedom for each mode? So only one mode, right? So this atom vibrate, but I put two for this atom. Why? No, I'm considering a 1D chain. Okay, where the okay, so first of all, so here there is a catch. Okay, so first of all, the three atoms. Okay, that's why this is three. Okay, because it's a 1D, so they can move in a directions, three atoms independently. So that's why the 3 degree of freedom for the translational case. For the rotational case, so it's basically, yeah. So for rotational case, they can rotate. I mean about the x-axis or about the y-axis, right? So that's why it's two. So now it's not clear. Okay, let's discuss in this way that okay. So first of all, I consider the translation mode. Okay, translations. For translations case, I consider only kinetic energy, right? So that means the molecules have m v x square. Okay, and the second one is also half m v x square, and third one is also half. Yes, so I can consider in this x directions, y directions, and z directions on the particular directions. Yes, vy square and then v half m vz square, right? Because in the so this is basically linear atomic molecule for each directions. Yeah, for each atom. Full systems. Okay, not each atoms. So three atoms, and that is basically molecules. Okay, and I want to calculate the degree of freedom of the molecules. So that gives you 3/2. So each gives you half kbt. So this gives you half kbt. This gives you half kbt, and this also gives half kbt, right? Because all are the vx square, vy square, and vz square. So therefore, the total E, this is basically, and if translational, then if translational degree of freedom is 3, right? And the energy for this if translations is basically 3/2 kbt. Now for rotation, now I am coming to the rotation. Okay. So for rotations case, they can rotate about the, so if let's say consider this is z directions, they can rotate about the y x axis. So let's say they can rotate about the x axis, the corresponding kinetic energy half ix omega x square. Okay. And they can also rotate about the y axis, iy omega y square. Okay. This omega is the angular velocity, because now your the molecules is placed along the z directions. Okay, so they can rotate about the x axis or about the y axis. Okay, so it's the only two modes. So each mode gives you, so that means the rotational mode is also 2. So if rotational degree of freedom is also 2, right? And E for this if rotational is basically 2/2 kbt is kbt. Now the vibrational, okay. For vibrational case, so this is a 3 atom, so only middle one can vibrate. Okay, let's say it's vibrate along these directions x. Okay, so what is the yeah, because the other one is fixed. Yeah, so basically if we consider a systems the triatomic molecules where the if we increase the temperatures, okay, or at some higher temperatures, only one, because it's a relative motions. Okay, so if we fix the two endpoints, then the middle one can vibrate. Okay, or you can fix other two, then the third one can vibrate. Okay, so at a time, so yeah, three can, but no, I mean yeah, so basically this is not a independent degree of freedoms. So basically if you say that, okay, so this one is also vibrate and this one is also vibrate, but I will say that, okay, so x1 minus x2 by common mode. So then the only one vibrational modes is there for if you fix the other 2 points. Okay, so then this is basically half m Vx square, but in this case, since they are vibrate, let's say they connected through a spring, so there is a potential, right? So that is also, let's say, half kx square. Okay, because if it is connected by a spring. Okay, so now for each vibrational modes, so your f vibrational mode, it gives you a kbt, right? Because the two modes bx square and x square, so that gives you a 2 by 2 kbt. So it's kbt. So each vibrational mode gives you a kbt. Okay, sorry, I mean the e energy. Okay, energy for each vibrational modes. Okay, it's basically gives you a kbt. Okay, and f of vibration, f of vibrational 2 for each mode. No, only one mode. For each mode, the two vibration degree of freedom is 2, because the Vx square and Kx, so there is a potential and as well as the kinetic energy. Okay, so that is very important. So for each vibrational mode, so we have a 2. So one translation mode, we have a 1 degree of freedom, but the vibrational mode, for each mode there is a 2 degree of freedom, where X and Vx. Okay, so that means so that is the total degree of freedom in this. Vx, Vy, Vz. No, that is already, I think, considered na, here. So, so this is along a linear molecules. Okay, why you say consider they are vibrate along the y and z directions? Yeah, X is fixed. It's a linear molecule. Okay, so the total degree of freedom is basically 7. Okay? 3, 2, 5, and 7. So linear triatomic molecules, the total degree of freedom is 7. So in this way, you can compute the degree of freedom for other molecules. Okay. So let's do one more problems, that is basically yeah. So let's say we have a these types of molecules that only this. Okay, so what is the degree of freedom? A and B, two atom. Okay. So in this case, the number of degree of freedom F is 5, right? So there is no vibration. Okay, so in this case, the number of degree of freedom is 5. So if there is a 2 only two atoms in a molecules. So it's basically only translations or rotational. Okay, but no vibration. Let's say we have a this kind of molecules that four atoms in a molecules. Okay, what is the how many number of degree of freedoms are there? It's not 15 because 3 is the translational is 3, right? And rotational is again 2. But now this mode can vibrate and this mode can vibrate. So for this mode is 2, for this mode is 2. These are the vibrational mode. These are the rotational mode, this is the translation. So once you fix the translations, now they can rotate or vibrate. So in this way you can compute the degree of freedom, right? So in the previous case, so I mean if you say that, okay, so first of all they are aligned in z directions, they are aligned in a x directions, they are aligned in y directions. So three possible orientations, sorry, three possible aligned, I think linearity. So that's why there is a 3. Now if you fix one, now they can rotate in x about x axis or about y axis if they aligned in the z directions, right? If they align in x directions, they can rotate about the y axis, they can rotate about the z axis. Okay, so I have to fix the translations and to compute the rotation degree of freedoms, right? You cannot change the simultaneously, right? So that's why you calculate the degree of freedoms. So in this case, so once you fix the translation, that is 3, and they can rotate about the, let's say, x axis or about the y axis if they are aligned in z directions. So that's why this is a 2 rotational, 3 translational, 2 rotational, and these two, let's say I can denote it that this one is a CD AB. So the vibrational degree of freedoms of C, A vibrational degree of freedom for C, and this one is a vibrational degree of freedom for D. Yes, the linear vibration, this kind of things. This is the linear vibrations. Okay, so it's basically only, let's say, x directions. I can denote it that this one is x or z, whatever. Okay, and the spring constant is k. So this molecule, so the middle one is can vibrate. Okay, the end one is fixed. No, it cannot rotate about the own axis. No, it's a linear molecule. How they rotate about your own axis? They can rotate about the perpendicular axis, but not own axis because they are aligned in the directions, right? How they can rotate about in own axis? Because three molecule atoms in a molecules are that's why the molecules, so atoms are rotating, not the systems are rotating, right? And this is not a degree of freedom, so because if they are tilted these kind of things, then you can say that, okay, so they can rotate about this axis or things. Yeah, so but that is not a degree of freedom system. No, that is not invariant for systems, because that is not change your system. So yeah, so in this case the total degree of freedom is basically 9, right? Only middle one can vibrate, okay, independently. So now if you consider a gas, so for a general results, so let's say consider a gas mixer. So I consider a gas mixer of n1 mole of gas, n1 mole of gas, let's say gas A, with degree of freedom N1 mole of gas A with degree of freedom is N1 F1, okay, and N2 mole of gas, the mixture of these two, N2 mole of gas, let's say this gas B with degree of freedom is F2. Now I want to compute what is the degree of freedom of this gas mixture, okay. So what is the degree of freedom of this gas mixture? So what is the, so this is the question, what is the degree of freedom of this gas mixture, okay. Okay, so how to compute this? So let's first consider so total internal energy of the systems. Okay. So first calculate the total internal energy of the system. This is basically the mixture of the two gases. So here is the system. No, it's basically the mixer. Okay, yeah. So gas A, gas B, there is a no interactions. Okay, so I will just I mean simply mix this the two gas. Okay, the N1 mole of gas A with degree of freedom F1 and N2 mole of gas B with degree of freedom F2. So what is the total internal energy of the system? It's basically the system of gas A and gas B, the mixer. Okay. What's the, so basically we just add the energy, okay, at the energy level. So E total. So what is the internal energy of gas A? F1 degree of freedom for yeah, so basically each molecules we have a degree of freedom F1. So n mole of gas A, so that means the, so half kBt, each mole half kBt, and there is a n1 mole, so n1 times Avogadro number Na times degree of freedom F1 plus n2 times and F2. So that means this is basically half I Na times kb, right, and then T n1 F1 and n2 F2, right. So your Na kb I know that half R T n1 F1 and n2 F2. So this is basically the total energy of the mixture of this. Okay. So energy is just simply add. Okay. So now I want to, let's say compute the mixer, right. So now so I think you know that what is the CV, the specific heat. So the specific heat is basically the specific heat at constant volume is del E total over del T at fixed volume V. So the specific heat of this mixture of gas is half times R N1 F1 plus N2 F2, right? It is derivative with respect to T where the volume is fixed. Okay. And yeah, so remember that the volume is fixed. So when we mix up the gas, so N1 mole of gas A with degree of freedom F1 in a volume V, N2 mole of gas B with degree of freedom F2 in a volume V. So in the same volume, I mix the two gas. Okay. So that is my total energy E at a fixed volume V. The specific heat is this. Okay. Now I know that what is my Cp minus Cv. it's basically n times r. Okay, n is the total number of total number density. So that means if the volume is same, so I can write n1 over v plus n2 over v r. So this is basically, I mean, yeah, so this is basically n1 plus n2, sorry, what am I writing? Yeah, so capital N1 over v, capital N2, and okay, and this is basically n1 plus n2 times r. Okay, so that means n equals to n1 plus n2. So the number density also simply add. Okay, so the total number density is n1 plus n2, the number density of molecule, sorry, of gas molecule A, and the number density of gas B. Okay, sorry, the number density of gas A plus number density of gas B, because both are same volume. So, and the total volume will also be. So now if we divide it by this Cv, okay, so that is basically Cp over Cv minus 1 is basically in R over Cv, right? So now know what is the Cv. Cv is basically this. Okay, and this is your Cv. So if you plug into this, and the gamma is basically the ratio of Cp over Cv. Yes. No, it's just a number density n1 by v1. So if there is a n1 of molecules are there in gas A, so it's the number density is n1 over v, right? Is the volume is v container. Okay, just a minute. So, I mean this n, yes, if you consider a unit volume, this is basically just a, I think, number of moles, right? It's clear. What I'm saying that n1, oh sorry, n1 or n2 is the number of moles, and in this case it just total number of moles is n1 and n2, and yeah, you are, no, n1 n2 is number of moles, right? I'll say, I'll tell that. So this is basically n1 moles and n2 moles of gas A and gas B. So yeah, so this is basically, yeah, so this is basically n1 plus n2 is the total mole of R, right? Yeah, I think it's now clear, right? Yeah, so n1 into a mole, sorry, this is yeah, so n1 into a mole. So and the total is basically n, because I mix these two. Okay, so the total number of I think the mixer is basically the n1 plus n2, and then yeah, so now you want to calculate the ratio of the CpCv of this mixer. Okay, so it gives that n R over Cv plus 1, right? So this is basically n R. Now I know what is the expressions of Cv. It's basically half of R, n1 f1, n2 f2 plus 1. So that means it's basically 2n plus n1 f1, n2 f2, right, divided by n1 f1 plus n2 f2, right? So R is cancelled. So now if we plug into this, that the gamma, the expressions of gamma, okay, I can write the next page. So gamma is basically 2 n1 plus 2 n2. So now I plug n equals to n1 plus n2 plus n1 f1 n2 f2 and then n1 f1 n2 f2. Okay. So this is basically n1 times 2 plus f1 and n2 times 2 plus f2. Okay. That divided by n1 f1 n2 f2. Okay. So now, so if the gamma is basically the ratio of Cp by Cp, and that can also written 1 plus 2 by f. So where f is the degree of freedom, okay, of the mixer. Right? Yeah, so collective degree of freedoms. So I can go in the backward. So first calculate the gamma of the mixers, and I can know that the gamma is basically 1 plus 2 by f. Okay, and f is basically 2 by, so it's basically gamma equals to 1 plus 2 by f. So now f is basically 2 by gamma minus 1. So once you know n1 f1 and 2 f2, you can calculate this gamma. Okay, and once you calculate the gamma, you can calculate the degree of freedom f of the mixer is basically 2 by gamma minus 1. Okay, no, if is not, if the total degree of freedom in the mixer, okay, that I want to calculate. No, f is not n1 f1 plus n2 f2, that's why I'm saying. So f is the degree of freedom that I want to compute of the mixer, right? So that's why I first compute the gamma, okay, of the mixer, and I know that the gamma equals to basically 1 plus 2 by f. This is basically f mixer, okay, and this f is 1 by 2 by gamma minus 1. Now you can plug into these expressions of the gamma here, okay, and you get in complicated expressions of the f. Yeah, so that is the, I mean, so there is a derivations, I mean, that I will discuss in the maybe in the next class. So this is basically general definition. So if we just using this CP and yeah, so there is a general way to say, let me think, okay, how do I, okay, so this thing I can discuss in the next class. Okay, so the derivations of these things, so gamma equals to 1 plus 2 by, but I think there is an easy way to also maybe derive in the class if I not sure. Yeah, so can anyone, if you know this, can anyone point out this thing, okay, so how to get these expressions? Yeah, so this is basically, I mean, already it's there, right? If you look into this, okay, so let's say is gamma is basically Cp by Cp, and this is nr by Cp plus 1. So now if you consider a system where there is a only f degree of freedoms, okay, so then the f is basically nr, right? So half nr, right? So now you can get that gamma equals to uh, 1 plus 2 by f, right? Where f is half nr, right? Yeah, because I consider a system where there is a f degree of freedoms, and I can compute the same thing for this system, right? But in this case, you cannot just calculate f is basically n1 f1 plus n2 f2, right? N1 f1 and n2 f2. we just check. I mean, I am not just a minute. So just calculate 2 by gamma minus 1. What is gamma? N1, 2 N1 plus, sorry, I mean just N1 by 2 plus F1, right? And plus N2 by 2 plus F2 and minus N1 F1 and minus N2 F2, right? And in the numerator is N1 F1 and N2 F2. So that means 2 N1 F1 plus N2 F2 divided by 2 N1 plus 2 N2. Yeah, so that means, yeah, so it's basically N1 F1 plus N2 F2 divided by N1 plus N2. Yeah, that is it. Yeah, so this is it. Yeah, so that expected, because this is basically the mixer how to calculate. So N1 F1 and N2 F2 divided by total. Yeah, that's yeah, so this is the total F. Okay, similarly, let's say for examples, I mean I just take one examples for this. Yeah, so let's say for diatomic and triatomic, I mixer two, yeah, so two molecules. One is the diatomic molecules. Let's say mixer of diatomic molecules and a linear triatomic molecules. Okay, and a linear triatomic molecules. Okay, so what is the degree of freedom of the mixers? Okay, so first of all, what is the degree of freedom for diatomic molecule? Let's say F1 is the diatomic. So diatomic molecule, what is the degree of freedoms? No, for diatomic molecules, I mean just a 2 AB. Okay, I already discussed somewhere. Yeah, so this is basically 5, right? So it's a diatomic molecule. So F1 for diatomic molecule is 5 and F2 for triatomic molecule, linear triatomic. So it's very interesting that linear triatomic 7, right? I calculate somewhere. Yeah, so this is basically, so this is a linear triatomic molecules and I calculate 3 plus 2 plus 2 is 7. So yeah, so now I have to calculate the total degree of freedom. So total degree of freedom F, just using the formula N1 F1 N2 F2 divided by N1 plus N2. I take N1 is 1 and N2 is 1. All are the 1 moles, okay, of each molecules. So then it's basically 5 plus 7 by 2, right? It's 6. Yeah, it's not just N1 F1 plus N2 F2, right? So the total the effective degree of freedom is 6 of the mixer. Okay? So now we can calculate the energy, average energy, right, using equiparson's theorem. So your energy of this mixer, okay, of this mixer is basically F of mixer over 2 half cavity, right? Is here the same. So using equiparson's theorem, so it's basically 3 cavity. Okay. So in the next class, I will discuss some other problems. Okay, and basically related to the kinetic theory of gases. And if you have any questions that I mean get in trouble to solve your assignment problems, or if you have any more question from this class, you can ask. Yeah, so I strongly suggest that if you have any questions, you can ask in the forum, okay, course forum. Okay, so if a time permits, I will get the answers on the forum. But if not, then definitely I will discuss in this in the problem solving sessions every Sunday at 4 p.m. So, okay. First, I will discuss the questions from the forum. So then I will address your questions. Okay, you can also ask the questions directly here. Okay. Okay, if anyone have any questions, so you can ask. Otherwise, I'll stop the meetings. Okay, if not, yeah. So if anyone have any questions, you can ask. Otherwise I stop the meetings and we'll meet in the next Sunday at 4 p.m. Yes, if you have any questions, Assis. Yes. So yeah, okay. So the degree of freedoms of a triatomic molecule. So I am considering a linear triatomic molecules, right? So let's say I have a system. So there is a three atoms that is placed on a axis. Let's say z axis. Okay. So what are the translational degree of freedoms? Is 3 because in 3D space they can translate along the x-axis, along the y-axis, along the z-axis, right? So now if you fix, let's say, z-axis, okay, what are the rotational degree of freedom? So that's why the first three came because of the translational, that is the Vx, Vy and Vz, the only kinetic terms are there, right? And that's why the F translation is 3 by 2. The translation degree of freedom is 3. Now the second one is the rotational. What are the rotational degree of freedom? How many possible rotations are? Yeah, so because if we align the, let's say, z directions, the three atomic molecules, they can rotate about the x-axis, right, or rotate about the y-axis. So that's why I think that the rotation, so is basically the omega. So that is your, let's say, this is a dot in the x-axis upwards. Okay, so this is basically half ix omega x square, right? And this is also half iy omega y square, where I is the moment of inertia, okay, and omega is the angular velocity, right? So that's why this is 2 degree of freedoms for the rotational, and in this case again the quadratic in the omega x and omega y. So that's why they are share half cavity. So it's total degree of energy is the cavity, right? Up to this point is clear. Now the vibrational case, right? So each, so in these systems, the, let's say, 3 atoms. So if you think that these 2 are fixed, then the only these can vibrate, okay, or these 2 fixed, only this can vibrate. So only one vibrational mode there, right? That is clear on. So for each vibrational mode, now let's say I consider these 2 are fixed, okay, as a reference, and only these, the middle one, can vibrate, right? So let's say, so this middle one can vibrate, okay. So now the vibration means, let's say I connected through a spring, okay, through this spring they can vibrate, okay, this kind of thing, okay. So each spring have a kinetic energy half m vx square, because they can the displacement is x. So I mean, if you have a mass m uh, atoms, okay, so they have kinetic energy half m vx square, okay, plus due to these vibrations they have let's say spring, so that there is a kinetic potential energy half kx square, right, for spring, okay. So that means in this case, for even if there is a one modes, but the degree of freedom is basically effectively 2. One is for this part, one is for that part, because I write that A equals to, for this mode is half kVt for this, okay, and for this another half cavity, because this is also half kx square, right? So this is also half cavity. Now I can write this total is basically this is equals to f by 2 kVt. My equivalence theorem tells you that this one is must be f by 2 kVt. Okay, so in this case f is 2. So that's why the vibrational degree of freedom, 2 for each mode. Now in this case, how many mode are there? Vibrational mode C can, if we fix A and B, C can vibrate and D can vibrate. So that's why for the vibrational mode C there is a 2, for vibrational mode D there is a 2. For each mode the 2 degree of freedoms for the vibrational case. Sorry. Because for the vibrational case the potential part also comes into the picture. Sorry. Yes, I'm saying that the temperature is high. So when I assign a problem, so its temperature is 300 Kelvin. But if we have a, let's say, assign a problem with a temperature 0 Kelvin, then you do not consider the vibrational modes. So that is very careful. Okay. But yeah, non-linear diatomic molecules, the vibrational degree of freedoms changes, because for rotation and I mean this is very complicated, because they can simultaneously translate and rotate. Yeah, rotational is 3 because 3 Euler angle kind of thing. So it's basically 3D points. Okay, so this they can rotate about 3 axis, not 2, right? That can one of the changes there. And other for vibrational case also it will be difficult. Yeah, I'll think about it, and I'll try to answer in the next class, right? So for a non-linear diatomic molecules, yeah, that's a very good questions. Yeah. Okay, so any other questions? It's not. I mean, the vibrational mode actually is that. I mean, there is a no specific. Uh, I mean, on the temperatures, but if you have a high temperature, you consider. But the cutoff is actually. I mean, it's a bit depends on a system. But I mean, this. But you don't worry about the cutoffs. About I mean about the room temperatures or above the room temperature, you can consider the vibrational modes. Okay, not greater than 0. Yeah, I mean, you just yeah, I mean, this cutoff is basically depends on other properties, but I mean that is vary to systems. Okay, so yeah, but I mean, if you have a high temperature, I mean around the room temperature, you can consider the vibrational degree of freedom. So, but if you exact cutoff that, but which temperatures I mean, there is always gap, right? I mean, there is always boundary that after which I can consider vibrationals below. Okay, so that is there, but so that's why there is a plot. I mean, this is basically, yeah, so there is also experimental determinations of this plot. I mean, you do not look into, so this is basically plot is something kind of this thing, and then somehow these and these, and then somehow these of these. Okay, so this is basically, it is basically temperature dependence, and these three are at the, this is basically 3r by 2, and this is basically 5r by 2, and this is basically 7r by 2. So when you consider a vibrational degree of mode, so its temperatures is very, when somehow it's greater than this point, okay, so you can consider the vibrational modes. Okay, and also if very low temperatures, the rotation is also not considered it. Okay, I mean, I'll tell more about on the next class. Okay, so this is basically, there is some plots. Okay, that is also tells you that why we consider the vibrational modes. Okay, yeah, that is also very good question, sir. So I'll tell you these things in the next class in details. Okay, so these plots basically. Yeah, and also if you have any questions you can also ask in the forums, okay, in the meantime, so that I can also look into these your questions and prepare and try to answer your questions here. Okay, yeah, so it seems that there is no other question, so I'll stop the meeting. Yeah, okay, see you on next Sunday at 4 p.m. Okay, okay, bye bye.